Okay. We just now need to talk about like partial orders. The reason is that in set theory, like a lot of the properties we care about for the natural numbers, the integers, the real numbers involve less than or equal to. So like, for example, if we want to express every non-empty subset of n has a least element. We want to say something like, we want to talk about how every non-empty bounded set of R has a least upper bound. Okay. We want to talk about things like that. Okay. Well, that means we need to talk about, well, non-empty is fine, but we need to talk about bounded, least upper bounds, least elements, and things like that. There's other issues we need to deal with too. Okay. So first, let's define what a partial order is. Less than or equal to is kind of our prototype for a partial order. Okay. Okay. Let R be a relation on A. If R is reflexive, transitive, and antisymmetric, then R is called a partial order on A. Examples: less than or equal to on the real numbers or the natural numbers or the integers or the rationals. Divides on the natural numbers. The subset relation on A. Recall, let me just remind you what that means. Subset relation on A is just, well, X is related to Y. If X and Y are in A, and X is a subset of Y. Okay, this is transitive, antisymmetric, and reflexive. Good. Known as equality on A. Okay. Because sometimes it's better, sometimes we want to talk about less than, strictly less than instead of less than or equal to. We have to talk about a strict order. So what is the difference between less than and less than or equal to? Well, instead of being anti-symmetric, never less than A, you know? Okay, so definition, we call that asymmetric. And R be a relation. R is called asymmetric if I have the wrong thing, sorry. But basically, if A, then B is not related to A. Sorry, I had the wrong idea there. That's okay. 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 So a relation that's transitive and asymmetric. So if R is transitive, just like less than is transitive and asymmetric. And we think of the difference between less than or equal to and strictly less than. Okay. And just like less than or equal to and less than, for every partial order, we get a strict order. For every strict order, we can get a partial order. Okay, so let R be a partial order. Wait, let me use a different symbol. Let me use a more illustrative symbol. Let curly less than be a partial order on A. Then define curly less than the curly less than is going to be A less than or equal to B, and A is not equal to B. Okay. So you can take a partial order and get a strict order by just saying but not equal to. Okay. And you can do the same thing to get from a strict order to a partial order. So I don't know if we have, let's take a strict order on A. Then you can define A less than or equal to B if and only if either A is strictly less than B or A equals B. Okay. Okay, and then we have a theorem that says that less than or equal to be a partial order on A, then strictly less than is a strict order on A. And let strictly less than prime be a strict order, then less than or equal to prime is a partial order. Between strict orders and partial orders quite easily. Okay, and then you say that they correspond. Okay. And we're not going to prove this. If you want 2.53, because apparently in this section there's like many definitions. Okay, the different definitions. Okay. Which is, I hope, is a relief. So let's take less than or equal to. So we have a definition. Let's take a partial order. on A. Then A and B are comparable if either A is less than or equal to B or B is less than or equal to A. Having a partial order where any two elements are comparable is quite special. Oh yeah, I guess I should say what is incomparable. If neither B or B is less than or equal to A, then A and B are incomparable. Okay, and a partial order in which any two elements are comparable is called a total order or linear order. So, I'm sorry. Can I go back to the page before? Yes. I hope that you mean this page. Oh, the ending, sure. Okay, and now I will switch. Okay. Okay, sorry about that. Probably I didn't scroll down enough. I ran out of my my better pages, or the pages that I prefer. Okay. So, yeah, most partial have this property where you'll have two elements that are not comparable. As an example, let's look at the subsets of 0, 1, 2. So let's look at the power set of this set 0, 1, 2. That is the empty set, all the singletons, all the way up to the set okay. That's the set A. All the subsets of this set with 3 elements. Okay. And then we have the relation subsets of A, like the subset relation on A. So we look at this. The empty set is a subset of middle A for all A. Okay. But you have lots of things that aren't related to each other. So the singleton 0 is not a subset of the singleton 1, and similarly, the singleton 1 is not a. So that tells us okay. So a partially ordered set in which everything is comparable is pretty special. Let A be a partially ordered set meaning it's a set with a partial order on it. Partial order less than or equal to. Okay, and then we just call it a linear or total order if any two elements of A are comparable. And less than or equal to is called a linear order if for all A and B and A is comparable to B. Oh, I went too far up. Okay. Linear order or total order. Okay. Just a few more definitions left, but we'll just, chains. We have to talk about least and greatest elements. We have to talk about upper bounds and lower bounds, maximal elements, minimal elements. And these are all related to each other, but they're all like have subtle differences. Okay. And then after we finish with all this notation, then we can finally do what we want, construct the natural numbers and show that it is we want it to have. Okay. So I will stop there and thank you everyone for staying with me. I'm going to kind of, say goodbye now. Okay. Have a good afternoon, everyone. Okay, bye.